We're now at a presentation with tools for kids. So I'm now going to talk about tools for engineers. ASICs, and ASICs is a four-letter word for application-specific integrated circuit, but it actually is broader meaning or a changed meaning, so you just use it. By the way, I also want to thank Wayne, because normally at the PIRA, I was on the list for the PIRA, which is a follow-up of Pandora, to present here, but it's not ready yet. So I borrowed Wayne's. So you can consider this talk as sponsored by KiCad. And I'm working at IMEC, and we do support services for making ASICs. So that's why I'm in the business. And I think I'm looking, can we make it feasible to make an ASIC with open source tools, and can you pay for it? So this is an overview. I first want to say that probably also chips want to be free. So 20 years ago, when the movement started, when FOSDEM started, all these things, they talked about information wants to be free. So I also think chips want to be free. So I want to discuss my dream, and then how I'm trying to achieve it, and then I will focus on the toolchain here in this talk to see what is the status. So 20 years ago, people started the Linux movement, which is one of the big contributors to the open source movement. And there people could just hack at night at their PC and Linux, for example, and a lot of people that just could do a lot of things. But up to now, you cannot do that for ASICs. So custom ASICs have higher startup costs, but now maybe time is saved. You have crowdfunding, so you can share things. So maybe if you have some startup costs, you can share them by crowdfunding. And you can do distributed development through GitHub and GitLab and these kind of things. So I have a dream. So what is my dream? My dream is to be able to do low volume open source ASIC service. If you look at normal ASIC production, they target high volume, so they have high startup costs, but low per unit costs. And you have to earn back your startup costs with selling a lot of products. And these startup costs are mass costs, the tools you use to do the chips. The engineers who work in it, they also want to get paid and have food on the table. Also the IP blocks themselves you will need to pay. And also the first thing, before people want to talk to you, the first thing you have to do is sign an NDA or so. So that's also not very open source friendly. So what I want to target is a service where you could have products made. So I mean full boards with less than 100 euros if you order around 100 boards. And if you go in volume, then probably the prices will drop a lot. So how to achieve that? First, we need an open source RTL to layout flow. So not try to reinvent or repay for the wheel. So the IP blocks also. Hopefully we can pool then also making the chips. So people already do that for wafers, but like I said, the fine print is often not easy for a normal guy to do. We also need the EDA flow, which is push button, so that people who write RTL code are mainly experts, and you need a lot of time, and that should be you should try not to have too much time to get into the flow. And also, somebody should be in between the real foundry so that they can see that everything legal is okay and that the guy who writes the code doesn't have to take care of that. So I'm doing a pilot project. It's a crowdfunded project. And the purpose of that is to find out, to get the first set of reusable cores, to test the flow, investigate where all the startup costs are, and where we can do the reduction, and also look at what is from legal side needed or wanted by the foundries. And this is the retro microcontroller, I call it. It has a Z80 core, a MOS 6502, and a Motorola 68 cores on it. But I'm not going to detail in this one. There will be a talk next tomorrow in the retro Kubernetes dev room where I will detail this part. I'm just now focusing on my experience I have with the toolchain, the open source toolchain. So what is an ASIC toolchain? Is that you have RTL code that you develop, synthesis, layout, sign-off, production, test, product. I will go in detail further. So let's first discuss, we have seen FPGAs in a few previous presentations, and there also Tristan already covered it. You have the fixed programmable blocks. So you have a fixed thing, and then you program the logic blocks or the IO blocks and the interconnects. But an ASIC is made with what they call standard cells. So each standard cell has a certain functionality. There's an NAND gate, and half adder, and a flip-flop. And then you assemble a lot of these on a chip, and you make a chip out of that. So that's the ASIC flow. And you can understand that the tools that you need to use for an ASIC flow are different than for an FPGA flow. For up to the logic part, RTL development, simulation, these are similar, but from then on it starts to become different. So what are the tools you need? For RTL development, you have to type in your code. You want to simulate it. Maybe you verify it on FPGA. Even formal verification, people are working on that now. Synthesize is actually your RTL code, which is event-driven code that you then transform into a netlist of the standard cells. That's what's called synthesis. The next step is layout. So there are two steps that you have to do. Is you place your cells and then you route into it. And then you have some special nets that you have to treat specially. You have the clock tree synthesis because that is to be connected to a lot of things. So you need to treat that differently. And also the power connections you have to treat differently. And that also has to be done by your place and route tool, as it's often called. Then your place and route tool has done, and then before you send it to the foundry, you do sign-off. And this is to be sure that it will work when it comes back from the foundry, because you pay a lot of money. And there are a lot of three-letter words used there. You have the DRC, which is design rule check. This is rules on the layout that the foundry gives that you have to obey. And if you don't obey them, then they will just reject your chip. Then you have layout versus schematic. During synthesis and layout, people can also transform your chip, your design, but then you have to be sure that it still does the same functionality. And then you do layout versus schematic, and also later on the logic equivalence check. Then also you probably want to meet certain timing. You want to run this at 100 megahertz, so you have to check the timing of your chip, which is called static time analysis. Power, also IR drop. So a lot of things are consuming power, and it means that the resistive network of your power will cause voltage drop, and you have to be sure that the voltage doesn't go too low on your chip. And then you also have the problem with scaling down, that signals are coming close to each other. If one signal can influence a signal next to it, so it can have crosstalk. And you have to check all these things if nothing is wrong with that. Luckily, for mature nodes, for older nodes, you need much less strict checking than for next generation nodes. So the tools become more important for state-of-the-art nodes. Then, after you have checked everything, you tape out to the foundry, you wait a few months, you pay, and then you get something back. And then you have to test. First, you can do it functional test, just run program it, run it like it used to be, and see if it works or not. But also, they also test it with ATPG with our test patterns that they just ran through the things to see that if there are no shorts or opens in your circuit. And there are tools for that to do that automatically. So now let's focus on open source tool chain. First of all, I started assembling my cores. I had a T80 and a T65, which is a Z80 and MOS 6502 compatible. They were in VHDL, and then at the AOI 68000 core, and this was in Verilog. So it means I need to be able to put two different languages on the same chip. So, and I think if you want to have a vibrant open source IP portfolio, this is a general requirement for having an ASIC toolchain flow. You should not in advance eliminate IPs because they are written in a certain language. So I'm an old school guy, so I still use Emacs for editing. And then I use proprietary FPGA tools, also the Quartus and EDA, and now we have Vivavo of Xilinx. For simulation, I use CocoTB, which is a coroutine test bench feature for Python that you can couple with normal simulators. The Icarus Verilog for Verilog and GHDL for VHDL. But for mixed language, I don't find anything good yet. So I do still use the model sim which is provided by the FPGA tools for that. For synthesis, you have Yosis from the QFlow for Verilog, and I have access to the Verific parser which provides VHDL support. So there was Alliance from France for the University of Paris that was done in VHDL, but it didn't follow the new standards, and this course used the new standards of VHDL, so I cannot use that at the moment. And also Tristan told that GHDL Synth Beta is still mainly a proof of concept, so it didn't support a lot of features that were needed for my course. So for layout, you have QFlow, the tools there, you have Greywolf and QRouter, and then you have Coriolis, which is also now developed in the University of Paris, and they have 3 tools there. So I had my course, I had the RTL codes, I synthesized them, and I put them through the tools, and I see that there is still room for improvement, but I'm in contact with both authors of these tools, and I'm convinced that this is not a bottleneck. So they are very real nice people, and it's just because I'm using a new node, a new technology that they haven't used before, that they have to do some setup, and that's not a problem. So I don't think that is still lacking for the flow. Then you have the sign-off. So yeah, so the DRC LVS support, you have in Lambda, in Magic, and in Electric, but they are quite limited. Of course, I'm using all the technology nodes, so the requirements are not that high. Production, I'm looking at different foundries, TSMC, onsemi, 0.35, 0.25 technology. So the silicon starting costs start from below 10,000 euro or dollar. And you can also have features like 5 volt or higher voltages even. So it should also be perfect for analog design. But when you have very low volume, that's not the only cost. You have also other. So they have a minimum area that you need to take, and then you want to subdice them, and that will cost money, and that costs more than the die itself, than the 1,000s of transistors you pay for, or cheaper than just subdicing the die. And also to start up the setup, so packaging. So to package your chip in a package, they start with a few thousands of setup costs. So you need to sell a lot of things to get that in a good find. So if somebody has references that want to do maybe packaging for a higher unit cost but lower setup cost, I'm all ears for that.
What about chip on board?
I also investigated that, but also there setup cost is the ones I had in contact with for chip on board, they had an engineer next to the tool all the time, and you pay the engineer, which is also a lot of money. But if you have references there that people want to do for low volume chip on board, I'm all ears also. So for tests, I have a GTAG interface where you can do boundary scan. So it means that you can put IOs in a certain state, so you can just test your PCB. For ATPG, the logic is small enough that I will just test it with programs that are running on the CPUs to see if the functionality is okay, and test the memory that way. So for the PCB tool chain, I'm using KiCad. You say it's sponsored by KiCad also. So it has a lot of features, but sometimes I still have the feeling I'm fighting with the tool somewhat. It's not, even for an engineer, to me it's not user-friendly. But maybe that's because I'm used to other programs with other ways of doing things. So maybe I haven't used it enough yet. So we'll see. For production of the PCBs, I will go to probably to Euro circuits. There, it's European. I think it's in England based. You can just upload your KiCad file there, and they will give you a quote. And they even have now providing assembly services, and so they can do them. Test. So for testing, I am planning to do eating my own food. So I'm planning to use an FPGA board with a digital microcontroller to test actually the boards that I will make. So to come to the summary, is an ASIC made with fully open source toolchain possible? Yes, I think it's possible. For the mature technologies, certainly. But I think we should try to get some renewed effort in mixed language support for the tools. For smaller nodes, new tools are needed for sign-off and test, but also there the setup cost will become higher, so probably the older nodes are good enough and you can do a lot of things with them. Is it affordable? I think it should be affordable for crowdfunding low volume projects. And if you have reference to reduce the setup costs more, I'm all ears. Okay. Any questions? So his question, how I have access to TSMC and onsemi. As I said, I work for IMEC, and IMEC is a VCA for TSMC. So they do provide services for IMEC. So on that side, it's also easy because I'm working there, so I can talk with the guys there. So, yeah. Yeah.
Are you using the standard PDK from University of Oklahoma for that, or is he doing something different?
So he's asking if you're using PDK of University of. No, I'm using the PDK of TSMC itself, and a standard cell library.
They provided one for Magic?
No. So you only need the Liberty files and the left files to be able to do synthesis and play that out, and these are available. Yeah, and these tools, the QFlow has support for the def and the left files and the .liberty files. Yours can read the .liberty file for timing information, and the placers can read the left file of the standard cell library.
Maybe I'm not using the right terminology.
There's some. Moses provides some libraries for QFlow for their for the TSMC process. Are those ones that you're using, or using something straight from TSMC?
No, so he's asking if I'm using the Moses libraries. No, I'm not using, because the Moses are based on Lambda, and I prefer the real dimensions. I'm just using a PDK that you can access from TSMC and a standard cell library. Yes.
You can download those from TSMC itself, or do you have to be one of the?
You can download them if you have signed an NDA. And before signing an NDA, you have to give the impression that you will order something. So, yeah.
Can you elaborate on the legal parts that you were mentioning? Because you said you were kind of you ironed out some of that.
So is the question about the legal part? it's mainly about these NDAs. If you sign them, what does it impact me? You don't know. And actually, in order to sign an NDA for TSMC, you have to have a company. So they don't want you to sign in person. And it had to be, so in Belgium you can work as an independent alone, and that was not enough. You had to really have an incorporated company to sign the NDA. And that's why I have now a company. So I want to have there an intermediate that I take care of these stuff and that you can just design. Of course, I cannot give you the standard cells, but I'm working on that to solve that. Maybe that I will do in the cloud, that you just test your code in FPGA, and then there is a Jenkins type of thing that just runs it through the synthesis, and then you get the results back, but you don't need the files to download the files to be able to do it. That's still open for discussion. Yeah.
Are there open source standard cell libraries that are usable with existing foundries?
He's asking if there are standard cell libraries and if they work with these existing foundries. There is, I think, one open source GPL standard cell library. If you go to vlsitechnology.org, there you can find these standard cell libraries. But they are GPL licensed, so it means that the code, all the RTL code also has to be GPL licensed. You cannot use it for a non-GPL licensed code. And I want to have something more usable, that the standard cell library doesn't decide which license you have to put on your RTL code. Yeah.
One more?
Have you seen this 17-year-old guy who's trying to make his own chips in his garage now, using LCD projector to avoid masks? So I'm hoping that we will get some 3D printer-like thing soon.
Actually, he's asking if I've seen the guy who's making chips in his garage. Yeah. I think I saw a video about that, but I want to stay away of chemistry, so I don't want to do that. It's too dangerous for me if I start doing chemistry. And anyway, yeah.
There is some 3D printed research papers that show how to actually print transistors using an inkjet printer.
Yeah, and about 3D printing, you have now, I think, inks that you can use for 3D printing where you can make some kind of schematic type of things. But that's maybe then how to make a transistor with that, and having hundreds of transistors on a sheet of paper, that's another question. Huh? Yeah. Yeah. Okay.
There has been a very short class communication congress from a guy from Switzerland who has made contact with the university in China, I guess in Hong Kong, to be able to use their chip production lab for doing 180 nanometers, 130 nanometers chips in small volume. Did you get any information about that?
It was where was it?
At the Chaos Communication Congress.
Yeah, but which university or in China?
I guess it was Hong Kong.
Ah, Hong Kong. So he asked if I'm aware about the facility of 0.18, 0.13 where they provided. I was not aware of that. I know that in Japan is also happening something like that. I met a guy at the University of Paris there. But there the language barrier was a problem. Everything was in Japanese. So, but if you can keep me in contact, I'm sure. So I'm still open for new. I haven't started it.
Switzerland,
Yeah.
living in China.
Yeah. So he's from Switzerland but living in China. Okay. Yeah.
Okay.
Right. Thanks. Yeah.